I'm from academic background, so you can expect something from the code, and more of that, I'm going to talk about why certain things are given in the code in a particular method. Okay? By the year 2030, India is expected to have 40% of population in the urban places. That is a whopping 600 million, a projected number. The urban space in India, as per the Ministry of Housing and Urban Affairs report, is 3.1%. So these two percentages are definitely not a match. What are we going to do? Maybe we can increase the urban space, but still, the construction of a tall building as a solution is definitely there. And even if you say like, we are not ready for very tall buildings, but still we have to be getting ready for that. And we have to do it efficiently. Let us look around the world, like how tall buildings are being done, like which material and systems they are using. As per the Council of Tall Buildings and Urban Habitat report, this is the trend over the years, over the decades, I would say. The amount of tall concrete composite buildings, it has reached up to 62% as of this decade. And if you look at China, almost 90% of their top 100 buildings are made up of steel concrete composite. So these two are like very specific structures, which is one made up of concrete filled steel tube, the other is encase column in their building systems. So why are they choosing these? So it has better structural performance, as everyone was talking about it. Like it has large column free space, stronger, stiffer and more ductile members, and it also promotes fast track construction. And this is one of the comparisons that I have made during my PhD. So you can compare like what is the strength of just a steel tube compared to if you are just filling it with concrete. So it almost goes up to like 2.5 times, which is 250%. And also it is versatile, robust and economical. So this is Taipei 101. Few of the floors were made up of composite, and after that it was made up of steel. So the top floors can be a little bit slender compared to the bottom, which has to be really stiff. So it is versatile, and it can be used for different types of structures, not only for buildings, like transformer towers, even the Statue of Unity, as someone was discussing in the morning. So it gives an overall economy to the entire system for all the stakeholders, like the designer, client, and the builder. So that is the economy that we want, and this system is going to present us with that. If you look at the Indian scenario, the top 100 buildings, I'm not talking about the rest of the structure, you can say that there are many steel concrete composite structures, but if you're looking at the top 100 tall buildings, only 2% is made up of steel concrete composite, which is the Sunshine Tower in Mumbai and Antilia. So this can be attributed to the steel consumption and the production in India compared to other countries, particularly China. But the national steel policy is want to make this, it want to double it by the year 2030 to 31. So definitely steel concrete composite is here to come, and we have to look at the best practices of designing this particular system. So in my presentation, I'll be discussing on, like basically I'm going to compare the steel concrete composite code, which is the Indian code, IS 11384, on par with European and American standards. The announcer was saying that I'll be talking about the British standard. It is superseded by Eurocode, so I'll be sticking to Eurocode as well as the American code in my discussion. I'll be discussing on these topics, which is materials and the kind of components which the code is covering, the design basis and analysis, the flexural member design. So all these have been discussed by the previous presenters, but I'll be pitching on like what is the difference in this code and the other codes. Shear connectors, compression member design, load transfer and load introduction. This is kind of new compared to the morning sessions, I guess so. The connections and joints, and some conclusion remarks. Okay. So this will be the format of my slide. So I'll be talking about the specification and comparing with the three codes side by side. So let us begin with the material limitations. Indian code is saying that you can use the material, particularly concrete strength, from M20 to M75. When it goes to lightweight, restrict to M60. EN code, which is the Euro code, it is giving the cylinder strength. What we're talking here, M20, 75, those are the cube strength. And cylinder strength wise 20 to 60, which is more or less the same, it is M20 to 75. And ASC also gives almost the same numbers. Going to the structural steel, Indian code says the structural steel should be less than 46 megapascal, and also the steel contribution ratio, it has to be from 20% to 90%. Only then it is called as a composite code. If it is less than 20%, it is not a steel concrete composite. Mostly concrete is going to take the load. And AISC gives FY restriction as 525 megapascal. It is on a little bit higher. And also the steel should be greater than 1%. This is not talking about the load resistance point of view. It is saying on the percentage point. And the rebar, the yield strength is should be less than 600 megapascal. Same in the EN. And here you see it is 550 megapascal. So why are we having all these restrictions? Someone can ask, like, why not more than M75? Why can't we use it? Because these equations, the capacity and all these specifications, these are based on certain test data. If you look at these data points, the compressive strength, the number of the frequency of tests which is done is particularly in this range. So the code is very well sure, like, okay, with this particular reliability or confidence level, you can use this grade for using these capacities, equations and these specifications. That's the reason. And the reason, if you're going for more test data, we can try for some higher strength as well. Next, talking about the concrete properties. So FCK, what is said in the Indian code is the cube strength. FCK is mentioned in Euro code also, but that is the cylinder strength. And AIC is directly giving it as FC dash, which is the cylinder strength. And this is the equation between the cube strength and the mean compressive strength. A small difference between these two codes, that is only because FCK is considered as cube strength in Indian code and FCK is considered as cylinder strength in the Euro code. Coming to the elastic modulus, IS 456 is what 11384 says that we are going to follow. But then for the elastic modulus, it is not using that equation. It is taking the equation from the Euro code. And again, there is a small difference in the formula, which is 12.5 and 10 because of this FCK difference. And this is the elastic modulus given as per the American code. If we put up a chart comparing all these elastic modulus, we can see that within the allowable grade, which is 20 to almost 75, if we use IS 456 elastic modulus or the new code, it is not going to be of big difference. And basically IS 456 is on the safer side. Types of members. So what type of cross sections code is giving the specification and capacity equations? So member considered in design. So the code is giving equations. It is covering all the flexural members, which is a composite slab or a profiled deck sheet or partially encased beam and slab. This is on the flexure side. All these cross sections for the compression member. So AISC is giving some extra equations for the shear wall. However, in American code, the partially encased beam is not covered. It is saying that it is not having the reliable adequate data and it is not giving any specification for these cross sections. And in addition, the Indian code is also talking about the precast slab beam systems. These are called as the filler beams. The filler beams are mentioned in the Euro code for bridges, not for buildings, but it is given in the bridges and it is taken in the new IS code. Okay, so that is all about the material properties and the kind of cross sections which is the code is specifying about. And now talking about the cross section classification. So we were talking about cross section classification for Indian code in the morning sessions. We are just saying how different is it mentioned in the other codes. So if we take this flexure cross section, so Indian code says that the compression flange, if it is adequately in contact with the concrete slab with the shear connectors, you don't have to classify it. We can just take it as class 1, that particular compression flange. Same with the Euro code, and American code is giving a little bit different equation, but more or less it is saying the same thing. It is talking like it is not really bothered about this compression flange. It is saying that this particular web, if it is within this particular limit, then we can go ahead with plastic resistance. Basically, the entire cross-section is compact. If it is having a partial encasement, then the Euro code is giving these classifications for your compression flange. Okay? So, compared to the steel cross-section, it is little bit higher. You can see those numbers. But in our Indian code, the numbers which are given is similar to IS 800 itself. I think there is a small error there, because when you are having a partial encasement, the points or the limitations should increase, and what the Euro code says should be the one, and maybe they will be giving it as amendment later. I'm not sure, because it cannot be just same as the steel cross section itself. AISC is not talking about the partial encasement. If it is having a full encasement and if the web is having adequate shear connectors with the concrete cross section, then you don't have to worry about the classification. It can be taken as a plastic resistance. And the same thing is mentioned in your AISC as well. If it is having a sufficient cover, adequate steel, and shear connectors, you can take it as class 1 and go ahead with plastic resistance equations. Now we are talking about the compression members, the cross sections that are filled, the completely filled ones. So this is the equation given in the Euro code as well as the Indian code. It is just giving the maximum limit. It is not saying like whether it is compact, semi-compact, or slender. But AISC is giving distinct classification, compact, non-compact, and slender, for both square cross sections as well as for the circular ones. So that is where these two codes are differing. So Indian code and the Euro code is giving the maximum limit, but then it is going to take advantage of the concrete enhancement or the confinement which is coming from the concrete in this CFST tubes. But AISC is not really taking advantage of this enhancement, but it is increasing the D by T limits. So these two codes are considering this CFST as the concrete is getting benefited, and AISC is saying that my steel tube is getting benefited because of my concrete infill. So if we just compare 1 to 1, here we are having 90, but if you are going to use AISC, it is going to say that compact can be increased up to 120. This is my non-compact and slender. It is basically giving us some room for going ahead with some larger D by T cross sections. Similarly, for the rectangular ones, we can have these numbers. Okay, I have just taken some 250 test data points and compare like how my Euro code and my AISC are getting compared. You can see that the AISC is having a little bit better factors. Similarly, this is for my flexure members, which is completely filled, and flexure AISC is giving the classification. Euro code and Indian are not talking about it. Getting into design basis. So Euro and IS are saying like we can go with a limit state method. That is the method which we are using for a regular RC as well as steel. AISC follows LRFD, as you know. And so the load factors and the material factors will be different because the design basis is slightly different. So how is it going to affect your calculations and design? If you are taking materials and you're dealing with loads in this particular location, you better go with that particular code. Okay, even if you want to design a shear wall, which is not mentioned in your Indian code or Euro code, you can use the IS code for the capacity, but use the load factors and the material factors, which is there in the Indian code. Getting into the analysis methods, all these codes say that you can go ahead with elastic analysis, but then you have to look at the second order effects, which is the P capital delta, the global buckling, and the P small delta, which is the local buckling. So when do you have to take this second order effects? If your P, the axial load which is coming, which is PD, the design load, divided by the critical buckling load, if it is greater than 0.1, then you have to do this second order analysis. And Eurocode says the same thing, and AISC is not giving such limitation. It is asking to do the second order analysis by any of these methods: direct analysis method, or effective length factor method, or the first order method with some magnification factors. So for P small delta consideration, so the code says that, the Indian code is mentioning that if your loads divided by PCR, actually there is again some error in the code, I guess so, which is greater than 4. Your PD cannot be greater than 4 times of your PCR. So I think if it is the design load divided by PCR is less than 0.25, which is 1 by 4, then you don't have to worry about this P small delta analysis. This is a local buckling analysis, and it is also in coherence with this particular load, this formula limitation which is given in the Eurocode, and AIC giving its own limitation. So if the load is less than so and so, or if the second order response to the first order response is less than 1.7, you don't have to worry about your local buckling things. And the plastic analysis, all the codes are giving room for the plastic analysis. Given the consideration, like if the materials are within so and so limits, you can go ahead with your plastic analysis. Joint types in the analysis, all the codes are saying like simple rigid and semi-rigid joints are allowed. If your connection is semi-rigid, then you have to model those connections in your maybe your ETAPS or any other software that you're going to use. Your connections, you have to model it according to these theories. IS 11384 is asking you to refer to IS 800, which goes with Zohar-Wade or Fry-Morris model. And AISC is saying that if the connection which you're choosing is falling under these categories, if it is pinned, you can just give the moment release and do the analysis. If the stiffness, if the stiffness of your connection is 20 times EI by L of your beam, then you can say that that particular connection which you have chosen is a rigid, and you can give a rigid joint in your analysis. Otherwise, you have to actually model your joint for your service limit separately and your ultimate limit separately, and then do the analysis. Eurocode is giving little bit different values compared to the AISC, but more or less the concept is the same. Going to flexure behavior, I hope you know what is happening with the shear connectors, the load resistance mechanism, and the assumptions is basically the assumptions that we have taken in IS 456 and also the 800. Eurocode also says that the assumptions which is taken in EC2 and EC3 to be considered, and AISC is referring back to ACI 318. And the effective width formula and shear lag, because of the shear lag we have to take the effective width, and the effective width equation is the same in all the codes. Only thing is in Eurocode and Indian code, it is giving a little more description about, so what should be the effective width if it is at the sagging location or at the hogging location, at the support, at this edge, like how it is going to be. It is a little more detailed. And the stress distribution, this is the main thing because it is going to create a difference in your capacity calculation. So if you're looking at Eurocode, the bending stress distribution, we are taking this rectangular stress block. In IS 456, used to have this parabolic stress block. So in this rectangular stress block, in Eurocode, the plastic neutral axis, your block is taken till this plastic neutral axis. And if you refer to this new code, which is IS 11384, your plastic neutral axis is little bit, your stress block is little bit above, or the stress block is not touching your plastic neutral axis. It is almost like your stress is not touching your zero strain level. Because why? Because the actual behavior is parabolic and you're just modifying it to a rectangular stress block, so you have to give some modifications. The modifications are mentioned like some alpha factor and eta factor in your Indian code, which is actually taken from the EC2. Not really sure why EC4 has not taken those reductions. These reductions are also mentioned in AISC. It is also not taking till the plastic neutral axis. The block is little bit reduced. And you can observe this change in the extreme stress value, which is 0.85 FCD. FCD is basically your FC dash, the cylinder strength divided by your partial safety factor of 1.5. So if you really put all those values together, it is going to be the same. 0.6 divided by 1.5, it is same in all the codes. And capacity equation, it says that equations are given in the annexure in your Indian code, and also in your EISA, in the commentary side, the equations are given directly for the ease of use for the designers. And EN is not giving, it is implicit, or maybe you can check some EN-based handbooks. So there are two more conditions to be taken care of during the flexure behavior if there is a high shear condition. So high shear condition, Indian code is referring to IS 800, where the demand to capacity, if it is less than 0.6, you can go with this plastic resistance. Otherwise, you have to give some reductions in your moment resistance capacity. But EN is actually giving this limitation of 0.5. So accordingly, the moment reductions are given in this equation. The moment reduction formula is the same in the Indian as well as the Euro codes. AIC is not talking about those things. And partial interaction, it is applicable only for the ductile members. And you know why this partial interaction happens. If your number of shear connectors are not as per the full interaction level, then you will be having the partial interaction, and this is allowable only in the ductile members. And specific equation and stress blocks are given in all the codes, and you can go ahead with this strain compatibility method or a simplified method for your partially interaction based beam slab systems. And Eurocode is also talking about one particular concept, which is the over reinforced composite beams. So mostly it may not happen in composite beams, but if there is a over reinforcement, then what to do? So Eurocode says that some reductions, you have to consider some reductions in your moment capacity. And if this neutral axis, if it is lower than 0.4, it is almost coming half of your steel section, then you cannot do this simple analysis. You have to go ahead with your nonlinear methods of analysis. So lateral torsional buckling is also addressed. It is also called as a distortional buckling. So you have the composite beam, you have the slab over your compression flange. So your lateral torsional buckling is basically to be avoided. But at the hogging locations, it can have a distorsional buckling. So the code is addressing those concepts by this giving the equation for the critical buckling load and other things. And some specification is given in the AISC to say, like, even if you're saying the slab and the beam is going to avoid your lateral torsional buckling, what should be the number of shear connectors to be provided? And it is also giving some details about how the propped and unpropped conditions to be accounted for. And AIC specifically says that the steel should be able to support the system in the case of unpropped condition, at least till the concrete achieves 75% of the strength. And CFST can also be taken as a beam, but it is not explicitly mentioned in the Eurocode. But AISC is giving formulas for CFST under flexure as well. And if I am using the EC4 equations, basically the plastic resistance concept, if I am going to extend it to CFST under flexure and comparing with the AISC equations, you can see that AISC is little bit conservative because it is going to account for compact, semi-compact and slender equation. All the equations are given separately in American code. So slab resistance I will just skip because all these are covered in the previous sessions. So you can go with partial interaction or the MK method, which is given in these codes if your slab is not having the full interaction. So AAC basically it refers to Slab Deck Institute's manual for all the deck related calculations. So we also have the stress limits, deflection limits under flexure for the serviceability checks, and the cracking limit. I'm going to just skip all these. Maybe you can have the slide for later usage. All these were discussed by the earlier speakers. So we also have the fire design for if there is a case of fire. If you are going to design for fire, then the longitudinal reinforcement. Even if it is CFST, you don't have to give the longitudinal reinforcement within this concrete. But if there is a fire design, you have to take it into account. And these three types of cross-sections are considered for the fire design. And the easy Eurocode is also giving this stress-strain equation in the case of fire so that a proper fire analysis and design could be done. And in AIC, what should be the fire loading, analysis, and the material properties as elevated temperature, all these specifications are mentioned. And it also makes a mention that encased column is the one which is actually considered as it has better fire resistance. But concrete fill tubes also have good resistance. Even though concrete is present inside, it will behave like a heat sink and it will keep the temperatures under control on your steel side. So vibrations, mostly the code is asking you to refer to some specialist literature for the vibration, floor vibration and other things. So shear connectors, we know like it's a function, the types, and when it is considered to be a rigid and a flexible shear connector. So it basically gives the load resistance mechanism, load transfer mechanism by undergoing yielding failure or the bearing on your concrete. So accordingly, the codes are giving its capacity equation. The same capacity equation is found in Indian as well as Eurocodes. AIC gives its equations based on the same load failure concept, but then the equation, the numbers are slightly different. If under the double action, this particular shear connector, the equation is the same, but when the concrete is going to, system is going to fail under concrete bearing, then the equation is slightly different. AIC numbers are a little bit higher compared to the other two codes. So shear connector equation is also given under combined loading when it is subjected to shear and also direct tension together. If the tension force is 1/10 of the shear capacity of your connectors, then you don't have to consider those tension forces. And AIC is also referring to this combined loading in your shear connectors. So how the shear connectors to be addressed, how the capacities should be addressed if you're not having a solid slab, instead you're having a profile deck sheet, there will be some reduction factor for your capacity. So the shear connectors can also be demountable when you're talking about recycling, circular economy, if you're using your eye girders, and then you don't have to go and cut it on. If there is a repair or you want to use it for some other usage, you can go for demountable connections. A lot of research is happening in this particular section. So whenever new shear connectors are coming, so what to do? The code is advising you to go with some test procedures. These test procedures are well documented in both these codes, even though the testing procedure is slightly different. Here in Eurocode, it is going for only this normal loading, the shear loading basically. In AISI, this lateral loading is also given during this testing of shear connectors. Okay, so till now I was discussing about the material, the kind of components which the codes are covering, and flexure. We were also discussing about the design philosophy, analysis methods, and the flexure design. Now I'm quickly getting into compression. I'll be a little bit quick on this compression because I have one more session for covering only the compressive design part. Okay, so we have two different types of system, encased as well as infill. So the code is giving, it is covering, specifications for all these types of cross sections. So, it is asking you to go with some general design method or a simplified design method. If you have to go with a simplified design method, then the selection of the materials or the cross section, it has to fall under these categories. It should satisfy all these conditions. The conditions are given in IS code and Eurocode are almost the same, and AAC is also giving certain conditions. And the equation for the encased is the same in all these three codes. And if you go to infill, as I said, the CFST is concrete and steel, both are getting benefited by this particular mechanism. But Eurocode and Indian code, they are taking advantage on the concrete side by saying materials. You can say that Eurocode is little bit not so conservative because the material safety factor which is taking is just 1. It is not even taking 1.1 for steel. So that is the reason why it is falling down. Okay. Otherwise, it's more or less the same for practical cases. You don't have to say like which equations I have to use for a practical scenario for the column design. So then the course is also talking about the beam column effect. We'll be discussing about this in detail in the next session, like how to design these columns. There is a small difference between these two codes. So here, there will be this slenderness effect or this axial load effect which is coming on your beam capacity, right? Bending capacity of this cross section. So the presence of axial load. So if you remember in IS 800, so you might have seen the P, whatever value, the load which is coming divided by its capacity plus the moment demand divided by moment capacity. That was the interaction equation, correct? But here you can see that P by P U, whatever it is, that particular part is not there. So composite is not taking into account of the axial load? No. It is taking in terms of this mu times D. It is taking care of this axial load effect. Okay. On the other hand, AAC is not doing this mu D. It will be just taking the axial load utilization as well as the moment utilization factor separately and will be adding it together. And the slenderness effect, it will be reducing this graph as such for taking the slender parts. However, in the Eurocode, it is going to magnify the moments. Okay, you can either say my axial loads have fallen down, or you can say that the second order effects have increased my bending moments by magnifying your moments. So that is the one small difference between these two codes. And this is another very important aspect, which is the load transfer in the infill tubes. So you can see that the load in a regular beam, it will be getting transferred through the steel tubes perhaps, but most of the test has been done as if the load is coming over your cross section uniformly. There is a large difference. That is where you have to concentrate about this, providing the shear connectors all along the length of your column. I'll be discussing about in length in my next session, and these are some of the connection methods for making the column splices for the encased and infilled. So these are for regular bolted connections. There are also new connections in the market like your blind bolts. Maybe you can go with a flush surface in that case, but test has to be conducted before using any new stuff. So these are the simple connections where the web is connected with your tube. Simple connections again, these are moment connections. The flange, web, and both the flanges are connected with the external diaphragm in this case. You can also go with the internal diaphragm. This is for the CFST and the encased ones. And you can give the fin plates, okay, instead of giving a complete internal diaphragm. This is when you're having a reinforced beam coming and sitting on your column. And So we were talking about the splicing, simple beam column connection and moment resistant connection. Then we have the pin column basis, then moment resisting column basis, which is a fixed base. So you can either go with this kind of system or the NK system. Someone was already giving it from some practical problems. So at the basement, you can go with from the foundation till this level. Even though from here we are having a CFST, it can be like completely encased throughout the height of your basement. This is one photograph from a project which came for proof checking, which is a data center in Mumbai. It is a G+10 building. We will be doing a design of one of the columns in that building in the next session. So this is how they have given their beam column moment resisting connection. So these are the two beams which is coming and getting connected with this column. Mostly we have seen that a beam will be directly connecting on this column face, but here it's a huge structure. It is a server supporting structure. So the column is also kind of huge, and they want to make sure that it is a completely rigid joint between the beam and the columns. And this is the anchorage system for the column, which is going till your foundation. And in all these connections, most of the connections, you are going with welded systems. But welded systems should not be the choice when it is getting into some fatigue loads or some high stress fatigue in the case of earthquake scenarios. These are the failures that were taken from the Tokyo earthquake in 2011 in Japan. So there are new research which is suggesting bolted moment resistant connections for these concrete fill systems. And whenever we are going for new systems, you have to look at the literature and see like what exactly is the stiffness of those connections. If it is falling at a semi-rigid, that should be taken care in the analysis, as I was discussing earlier. So these are some of the systems, and this is the shuriken bolt. You might have heard about it. So these kind of system can be used for tubular systems. And in conclusion, so the Indian code and the Euro code is almost the same. Indian code has taken most of the fundamental reasoning from the Euro code, keeping some main concepts from IS 800 and 456. And few of these clauses are much elaborated, like mostly the capacity equations and everything. You don't have to sit and work through it. All the equations are given, so for the benefit of the users, of course. So within the given material limitation, the code specifications are very safe to use, and you can see that the equations and the LRFD, the resistance factor, make your capacity little bit conservative compared to the other two codes. But you have to see that if you want to use for larger D by T, AISC should be your choice because it is allowing you to go for larger D by T values. If you are having thicker sections and you want to take advantage of this confinement which is coming from the CFST, you can go with Euro codes. So composite wall design is much more elaborated in AISC, and the connection design, ductile detailing, fire design, and the tests for the shear connectors, composite slabs, everything is given as mostly like annexures or some tests to be conducted. So, so that's all from my side. So let us use the code with lot of, you should not be reading between the lines. You should not take anything blindly from the code. Thank you.